Okay, thank you for watching these recordings. We are going to talk about a topic called the ratio test. So basically, the ratio test is a test that is used to test the convergence of a series. So the series, as usual, will write in the form of like this, where your n is to be summed from 1 to infinity. For the ratio test, it is only applied for a series where all the terms are positive. So you can't apply the ratio test to a series where the terms are not positive. Okay, so now the very simple applications of the ratio test is by looking at the ratio of the next term divided by the previous terms, and then you take the limit of this ratio to infinity. So basically, it just simply means you have a series which is a sum of a1 plus a2 plus a3, etc. Right? Okay, so then you assume that for every term in the series, an are always positive. So imagine that you take the ratio of n plus 1 divided by an, and then you take n to infinity. So these ratios would be a kind of ratio for the next term in the series and the term before that term. Then you take the ratio. So if the term in the next, if the term of a plus n is always smaller than the term before it, it would simply give you an idea that the sequence will actually go down to become smaller and smaller. Now, on the other hand, if the ratio of an and an plus 1 over an is not less than 1, but say larger than 1, it will give you an idea that the next term is always greater than the term before that. So when you go to infinity, you expect the next term will always keep on increasing. So you expect that if the ratio is less than 1, that means the term in the next term that comes will always be smaller than the term before it in the series. So at the end, when you go to infinity, then the values of the sequence an will just get slower and slower, and that gives you a chance for the series to be convergent. So if you look at another hand, situations where the next term in the sequence is always larger than the term before it. So when n goes to larger and larger in infinity, then you expect the next term will always become larger and larger than before that. So if you go to infinity, then you expect the last term will goes up to very large when n goes to infinity. So in such a situation, you don't expect the series to converge. Right? The series is made up of the sum of a1 plus a2 plus an up to a infinity. So if the term in a infinity is going to become infinity, then there's no chance for the sum to be convergence. Okay, so anyway, this is a very, very simple test, and it's easy to use. What you do is you just check the ratio of the next term to the term before it. Then you check the limit for this ratio when n goes to infinity, and you get a number. Right? So if the number is less than 1, then the series converge. If not, then the series will be diverge. Right? So you have only two situations. That is when we have actually three situations. When rho is less than 1, then the series will converge. If rho does not exist or goes to infinity, or when it goes to larger than 1, then the series will diverge. And if you find the rho is equal to 1, you can't say anything about the convergence of the sequence. We say the test gives you an inconclusive conclusion. So these are two examples. It should be actually quite simple to apply. What you do is that you just have to form a ratio. Well, we don't form a ratio. You just form the ratio of a plus 1 over an. Then you then you simplify the expressions. So this is an. So for a with n plus 1, you have an plus 1 plus 5 over 3n. Then you divide it by an. So an will be just 2n plus 5 times divided by 3n. So that 3n will then be brought up to the numerator. So here it will be 2n. I think there's something that I've gone missing. So this should be n plus 1. Okay. So you conclude this as saying this is just equals to, I think this is 2 plus 5, and this is the multiply with 3n. Right. So the 3n here and the 3n, 3 power n and 3 power n plus 1 downstairs will get cancelled off, and then you are left with a factor of 3. Then you have a ratio of 2 factor, which upstairs here is a factor of 5 plus 2 power n plus 1, and here you have 5 plus 2 power n. Right? So you have this kind of expressions. Then what you need to do is to take the limit. So this is what I am writing down just now. After you make some simple expressions, the ratio of the term n plus 1 to an is just a simple expressions that looks something like this. So what you need to do is to see if you can check out the convergence for this series. So there are many ways you can check the convergence of this sort of series. To check out the convergence of this term, it's not a series, actually it's a term, but n goes to infinity. We have learned a few tricks of how to check the convergence. Right? You can use the integral test, or you can use the other test that you can think of. Now, there's no fixed rule what kind of test you should use to check the convergence, as long as you can prove it convincingly. So the easiest way to do here is to pull out a factor of half from these expressions. So I would like to write this on a piece of blank paper and try to see if I can simplify this. So the expression I was showing you just now will look something like this. You have a factor of 3 1/3. Then you have 5 plus 2 raised to the power of n plus 1. Okay, maybe I should write it again. 2 power n plus 1 plus 5 and 2 power n plus 5. So what you want to do is to pull out a factor of n, because you know that I think this is what we call a generalized exponential functions, and then the exponential functions would look something like this. If ax is, I think it's called like exponential function with minus x, then this will mean that when x goes to very, very large, then the function will just drops out to infinity, to 0. So this is a behaviors of an exponential functions with a constant a, and when x goes to infinity, they just drop to 0. So just try to see if you can express or recast this expression into that form. That should be easy, because upstairs you have 2 to the power of n plus 1, downstairs you have 2 power n. Right? So if you pull out the factor of n, then you may get something. So that is what I'm going to do. I'm going to pull out the factor of 2. Well, I'm going to pull out the factor of 2 power n from the above. I get 5 plus 2 raised to the power of minus n. Right? You get so that downstairs is 2 power n times. Sorry, I think this is not quite true. I pull out the factor of 2 power n, then it gives me something else. So let me rub off my error. I can't rub off my error, so I have to write this again. Okay, so let me pull out this one. I'm not going to write the factor of 1/3, but I'm going to pull out the factor of 2 power n from upstairs, and also 2 power n from downstairs. So from downstairs, I have 2 power n, so that would give me a number of not this, but it will be a number of 1, and then it will be plus with 5 multiply with a factor such that this factor multiplied with 2 power n outside will give you 1. I think that is the downstairs. So upstairs, if you pull out a factor of 2 power n, then you still have 2 power 1, right? So this is 2 power 1 multiplied with 2 power n will give you 2 power n plus 1. And again, you have here, you have 5 multiplied with n minus, it's a 5 multiplied with, let me rub off this. So it will be 5 multiplied with 2 power minus n. Right? So that would be my expression. So I cancel off this one. So what I'm left with is these expressions. Yeah, so let me rub off again. I can't rub off this one, it's very weird. So anyway, I think you can see the trend now. So this is an expression with n. So when n goes to infinity, what happened to this term? 2 power minus n, it just drops to 0. So is this will drop to 0. But you have a factor of 1/3 outside. So this will give you a factor of 2. Then overall, the ratio of a n plus 1 divided by a n in the limit n goes to infinity is a number, rho, which is less than 2. Therefore, by the theorem of the ratio test, rho less than 1 means the sequence, means a series. It means a series that is shown here is going to be converged. So that is the first. Okay, so now we are looking at another example where you are asked to find the convergence for question B, which is these expressions, something that involves a factorial. So for this kind of questions, you can apply the ratio test, but in this particular case, the algebra dealing with factorial may not be very familiar with you. So I'm going to go through the details of the procedure, of the steps of how you can do these kind of questions. So first of all, you apply the ratio test by writing down the expressions of n plus 1 over an for the series that under investigation. So your expression would involve some complicated functions of n and also n factorial. Then in order to obtain the solutions from the limit when n goes to infinity, so that you can obtain the values of rho, you have to know how to deal with the factorial notations. So you have to then make use of some knowledge about factorials. So say what you mean by factorial is you have, say you have an n. Factorial, it just simply means n times n minus 1, n times 2, and then up to all the way up to 2 times 1 times, I think up to 2 times 1. So for example, 4 factorial is just equal to 4 times 3 times 2 times 1. So one of the very, very important sort of like the very, very important properties of this factorial is that if you have n factorial, this is the same as n multiplied with n minus 1 factorial. Like for example, if you have 5 factorial, is equals to 5 times 4 factorial. Right? So and then again, 4 factorial is the same as 3 times, is equals to 5. So 4 factorials is equals to 4 times 3 factorial and things like that. So say for example, n minus 2 factorial is just equals to the n minus 2 times the rest, which is the n minus 2, well, I should say n plus 2. Okay, so if it's n plus 2 factorial, then it's the same as n plus 2 times what? Times n plus 1 factorial. Right? So this is just a the properties of the factorial based on their definitions. So now let me work out the solutions for the power series for this particular case. So the expressions for n plus 1 over an based on the expressions of the series that we are considering is that your an is equals to 2n factorial multiplied with n factorial. So this is expression from an. I just purposely write an first before I write down the expression for a of n plus 1. So to write down the expression for a of n plus 1, what you do is just replace n by n plus 1. So according to the definition, this is equals to 2 times n plus 1, and the whole thing has n factorial in it. And downstairs for the a of n plus 1, it should be n plus 1 factorial and n plus 1 factorial. Okay, so that is n plus 1 factorial. Okay, so this is the expressions for the ratio. Then what you do next is to try to simplify it. So obviously the first thing I want to simplify is to simplify these terms. You cannot just simply cancel off the 2 or n factorial from that. So for example, you will be tempted to write that n factorial or n factorial divided by 2n factorial like this equals to what I'm saying. It looks like it is equals to n factorial divided by 2 factorial. Is it true? Okay, no, I think this is not true. Okay, so you can check it for yourself. You just cannot write it like that. This is not the correct way of doing factorial. You have to do the factorial very carefully by following the definitions of n factorial. So what you need to do is to cancel the correct term. Right? So for example, this should not be cancelled with the 2n, but instead, okay, let me rub off this circle. This should not be treated together, but we should treat this together with this. So I'm going to write down n factorial divided by n plus 1 factorial times n plus 1 factorial. Then there's another part which is 2 of n plus 2 factorial divided by 2n factorial. So this will be treated separately from this part. Okay. So let me move it a little bit. Okay, so here you have n factorial divided by n plus 1 factorial. So n factorial divided by n plus 1 factorial is just equals to n plus 1. I've already mentioned that. So when I do that, what I'm saying is that n plus 1 factorial is just equals to n plus 1 multiplied with n factorial. This is just what I have mentioned earlier on. So it is quite obvious that you have upstairs is n factorial, downstairs is n plus 1 factorial. So n plus 1 factorial is n plus 1 times n factorial. So the n factorial get cancelled off, and you have two such terms of n plus 1. And upstairs, we have to release some of the terms. So upstairs, what I'm going to do is I want to make the two, let me write a little bit here. What I want is I want to make two very simple thing. I want to first I see that there is a 2 here and there's no 2 in this term. Then I also have this factorial thing, so I want to get rid of this factorial. So what I have to do is that I just look at 2n plus 2 factorial. I want to make it to look like it is just involved in only 2n factorial in the denominator. So I am going to convert this, try to make it to look like 2n factorial so that it can cancel off with the 2n factorial downstairs. So what you do is just release the term. When I say release, it just means that you just take out the first term in 2n plus 2. This is a, sorry, it's not like that. So you just take out the first term. You will take out one term from that. What you left with is 2n plus 1 factorial. I have not enough place to write. Okay, there's a factorial term here. There's a factorial term, so maybe I need to rub off this one just to write it. Maybe I just write it downstairs. Okay, so that is just equals to 2n plus 2 multiplied with 2n plus 2 minus 1, because I have released one term from 2n plus 2 factorial. So what is left is you have one more term. You have one more term less in the original factorial. Right? So this is just 2n plus 2 factorial, right? Divided by 2n factorial. So downstairs is not changed. Then upstairs, so let me try to do it a little bit more. So again, it doesn't look like upstairs is expressed in 2n factorial. I have to release one more term from 2n plus 1 factorial. So to release the 2n plus 1 factorial, I release the term of 2n plus 1. Then what's left is you have 2n factorial. Right? So this is just what I have done. I've just rewrite 2n plus 1 factorial into this. Then downstairs would have a factor of 2n factorial. So that could then be easily simplified. You have almost there already. So now you can cancel off 2n factorial with 2n factorial. So what is left is 2n plus 1, and you have 2n plus 2. So that is the results from these terms. So I just scroll it up, and then I just have to fill up this expression here. It is just equals to this is just equals to this expression. So the expression is it will be 2n plus 1 and then 2n plus 2. I think that is what we have obtained. So this is the expressions of the ratio of a of n plus 1 to n plus 2. Right? So now it is almost there. We are now ready to take the limit. We're almost there to take the limit for these expressions. So if you look back at the PowerPoint, actually give you the results, which is like this. So this is the results that I have just reduced from the calculations, where I just shown you how you can get rid of the factorials. So we have these expressions. So you look at this one, then you just make some cancellations. You carry out the factor of 2. Then there's this factor of 2 get cancelled off, blah, blah, blah. So you go from here to here. You get these very simple expressions. So what you do with this, to take the limit. How do you take the limit? It's very simple. What you do is that, again, in order to take the limit of these expressions, you just pull out the factor of 4. So what you do is that here you pull out the factor of 4, you get 4 plus 2 power n. Then downstairs you pull out the factor of n as well. So it become 1 plus 1 over n, right? So n get cancelled off, then these terms will get to 0, this term gets to 0. So what is left is 4. It's actually quite straightforward. So now the ratio of this is going to be 1. So now you have a situations where for this sequence, the series made out of this sequence is going to not converge. Right? It looks like it's going to converge, but actually it's not. I said earlier on, I think I mentioned somewhere, I thought that, well, maybe you have 2n factorial. 2n factorial will go to infinity when n goes to infinity, and n factorial will also go to infinity. And now you have both of them joined together. So joining force of 2n factorial actually cannot beat the 2n factorial. 2n factorial will go to infinity much faster than n factorial join force together to form a square. Right? So it means that these terms will actually go to infinity much faster than n factorial squared. So as a result, then the series does not converge. So you can see this sort of argument. We can try to interpret these behaviors. Why is that the series for an goes to infinity? It doesn't converge because I think this is part of the reason. The 2n factorial go much faster than the n factorial square. Like n factorial go very fast, and 2n factorials and n factorial again, and n factorial square cannot even beat the to n factorial. So that is the example for this part. So thank you for your well, I've not finished yet. There's one more slides that is just to cautious to you that the ratio of R that you calculate earlier on. So you always form this and then you take the limit of, and then you try to find the limit. If the limit exists, then it doesn't mean that the series converge to raw. It's not at all. Okay, it just shows you that it's when raw is in existence and its value is less than 1, then you said the series would converge. But converge to what value? No, you don't know. If you want to know what is the series converge to, you can ask Mathematica or you can ask Wolfram Alpha. So you type in the expressions, then you get the answer. So in this sense, the test only allows you to have a qualitative knowledge on the convergence, but it do not give you the quantitative information about the convergence. Quantitative means you want to know exact what number is that. Qualitative means that you just know that it converges, but you do not know the values. Okay, so that's all for these discussions. We end our discussions for this recording here.